Okay. Hi. Good afternoon, everyone. So, this is the fifth week we are meeting for the course Fluid and Particle Mechanics. So, in this week, we will mainly solve the assignment problems which you have already submitted, but I will solve them in details. And if you have any confusion, you can ask me. So, let me go directly to the assignment problems. It will be very easy for you also to see. So let me start with the first problem. So here it's saying that uh, let me start it. So here it's saying that consider the figure below, and you have three stars of decreasing size. Okay, and these v1, v2 and v3 are, let's say, some sort of velocities which is uh, towards these stars in the same directions, and these stars are, as you can see, that they are decreasing in size but they are geometrically similar. Okay, that means in some way you can say that the ratio between the two, as we go from left to right, the ratio from this and this, ratio from this to this is equal to the ratio from this to this in terms of their dimension. Okay, so then, like, what are the options given? That which of the following statements are true? Shapes are given in the figure are geometrically similar. Yes, shapes are given in the figure are geometrically dissimilar. No, that is wrong. Comment about geometric similarity can be made only if the ratio of v2 by v1 and v3 by v1 etc are known. See, v1, v2, v3 are the velocities. So they are associated with the kinematics of the problem. Okay, so actually you don't need the information about the velocities in order to say that whether they are geometrically similar or not. Comments about geometric similarities can be made if the Reynolds number is known. Again, this non-dimensional number, Reynolds number, which is basically the which will show you the dynamic similarity. It is not about the geometric similarity or the kinematic similarity. Rather, the Reynolds number is the inertia force by viscous force that will represent some sort of dynamic similarity between the two problems, or between, in this case, to flow first three different stars. Okay, but these three different stars are only different in terms of their size, not in their shape. So that's why they are geometrically similar. So the correct answer is that shapes given in these figures are geometrically similar. It is the right answer. Okay, now let me go to the second one. So second one says that which of the following statement is wrong. Okay, so which of the following statement is wrong? Here it's saying that the kinematic similarity automatically implies geometric similarity. This statement is right. Okay, so when you have two kinematically similar problems, the geometric similarities is already inbuilt in that. That's why they are kinematically similar. Okay, the motions of two systems are similar if homogeneous particles lie at homogeneous point at homogeneous times. Yes, that is true. The motions of two systems are similar if for both the systems the homogeneous particles lie at the homogeneous points at homogeneous times. That's true. Dynamic similarity ensures that all forces are in same ratio and have equivalent directions between the models and the prototype. Yes, that is what the dynamic similarity is. Dynamic similarity talks about the similarities in terms of uh, force and torques. Dynamic similarity automatically implies kinematic similarity. Yes, if the two problems are dynamically similar, that means they should be kinematically similar also. Kinematic similarity requires that the models and the prototype have the same length scale ratio and same time scale ratio. Yes, so the same length scale ratio and same time scale ratio means the same velocity scale ratio. That is that is why they are kinematically similar. So statement 1 is true, statement 2 is also true, dynamic similarity is also true, dynamic similarity automatically implies kinematic similarity, that is also true. uh, Kinematic similarity requires the models and prototype have the same length scale ratio and same time scale ratio. That indirectly implies that they are of same like velocity scale ratio. So of course they are kinematically similar. In two geometrically similar shapes, the absolute value of angles will also be the same. Yes, that is true. That is why they are geometrically similar. So in terms of geometry, that absolute value of the angle should be the same. Yes, the flow condition for a model are completely similar if all the flow condition of a model are completely similar if all relevant dimensionless parameters have the same corresponding value for the model and the prototype. Yes, so the non-dimensional number representing the geometries of the two two problems, that means the geometries associated with the prototypes and the model should be the same. The flow topology or the kinematics of the flow should also be the same, and that's why the non-dimensional number representing the uh, kinematics of the problem for the kinematics of the flow for both the prototypes and the model should be the same, and also the non-dimensional number representing the dynamics of the uh, flow in case of the models and the prototype should also be the same. So that means this is also a right statement. All technical statements in this section are correct, that is also true. So this is all the technical statement made in these sections are also right. All technical statements in these sections are wrong. So the wrong statements of all of these statements is the last statement, because all of these, so it is, so you, so you have so you have been asked that what is the following, which of the following statement is wrong, and we see that all of these statements are right, okay, except the last statement. So that means the last statement is the right option for this problem. Okay, so let me go to the problem 3. So what it says, that uh, 1/6 scale model of an automobile, a 1/6 scale model of an automobile is to be tested in a wind tunnel at a speed corresponding to the prototype speed of 60 kilometer per hour, assuming that only inertial and viscous forces are to be modeled. Calculate the following. So what it's given, so you have a prototype and you have a model. Okay, so what is given, so it is given that both for the prototypes and the models, we are only concerned about the inertial force and the viscous force. So in terms of the dynamic similarity, we are only concerned about the inertial force and the viscous force. So let's say the velocity here is the, let's say, Vp. Okay. uh, so this is the prototype velocity. So velocity is Vp, length scale, some length scale is, let's say, Lp, and so that will do the job. Here the velocity scale for the model is, let's say, Vm, and length scale associated with the problem is, let's say, Lm. So you have given that a 1/6 scale model. That means given that Lm by Lp is equal to 1/6, that's what it is given. Okay. So what will be in terms of area? Okay, that means the uh, ratio of the representative areas between the prototype and the model will be what? Will be, let's say, Am by Ap will be that length scale square, so it will be 1 by 36. That's all. Okay. Now let's go to the problem. So here I wrote it, the required part. Okay. So as you can see that I have the models and the prototypes. So this has to be geometrically similar, kinematically similar, as well as the dynamically similar. Okay. So they have to obey all the three conditions. Then only we can successfully test the model in the wind tunnel with the actual prototype. Okay. So, and as mentioned in the question, that we are only concerned about the inertial forces and the viscous forces, not about any other forces. So let me go to the problem then. So what it says, that according to the question, which among the following numbers need to be same in order to perform the comparison? Okay, the inertia force by viscous force is the Reynolds number. So the correct answer is the Reynolds number. So okay, it is also given that Vp is equal to 60 kilometer per hour. It is given. Then what is the question, that what should be the wind speed at which the model automobile should be tested. Okay. So in both the cases the fluid is air. That's what also it is given. That means the uh, properties of the fluid in both the cases are the same. So what you have been asked, that what is the fluid around the models and the automobiles, around the model automobile and the prototype is the same and is air. So they are saying that what should be the wind speed at which the model automobile should be tested. Okay. So the Reynolds number for the prototype will must be equal to the Reynolds number of the model, as simple as that. Okay. What is the Reynolds number of the model and the prototype? So it is uh, velocity scale of the prototype into the length scale of the sorry into the length scale of the prototype divided by nu, that is the kinematic viscosity of the fluid, velocity of the model, length scale of the model divided by the kinematic viscosity. Is that correct? So the let me write it as kinematic viscosity of the fluid when we are in case of actual prototype, and the kinematic viscosity of the fluid when we are testing for the model. But in this case kinematic viscosity, that is nu p is equals to nu m. Okay, fine. So that means the Vm is equal to Vp into Lp by Lm, as simple as that. What is Vp? Vp is equals to 60. What is Lp by Lm? Is 6. 360 kilometer per hour. That should be the answer. Okay, that is the 360 kilometer per hour. Yeah. Okay, so this is question number 4, I guess. Yes. What is given in question number 5? What they asked, if the model drag at that speed is 510 newton, what will be the drag on the prototype? That is also an interesting question. So for the models and the prototype to be uh, dynamically similar, the drag coefficients for the both the cases should be the same. So what is drag coefficient? Drag coefficient CD is equal to drag force divided by half rho v square into some projected area. Okay, this A here, so this is my drag force. Yeah, sorry, I wrote the spelling wrong. So this is the drag force, this is my drag coefficient, okay. This is the projected area. Over which the projected area of the object over which the some flows are there, okay. So for the two model to be dynamically, so it is given that drag force for the case of model is equal to 510 Newton. It is given, am I right? For the drag force in case of the two problems are given as 510. For the model case, the drag force is 510 Newton, and it asked that what should be the drag force in case of the actual prototype. That's what they are asking for. So what will be the drag force in this case? So that means for dynamical similarity, CD for the prototype must be equal to the CD of the model. That's what it should be. So what is CD? So this is FD, drag force of the prototype, divided by half rho, the density of the fluid associated in the prototype problem, into Vp, the velocity, into that projected area in case of the prototype, should be equal to the FD in case of model, okay, divided by the half rho m Vm square into Am. Am I right? Yeah. So here fluid in both the cases, in both the cases are air. Here the fluid in both the case is air, okay. Thus rho p is equal to rho air. So what is the FD of m then? Sorry, I have to calculate the FD of p. Therefore FD of p is equal to FD of m, okay. FD of p is equals to FD of m into, it should be Vp by Vm square, okay. It should be Vp by Vm square into AP by AM. Am I right? Yes. So what is Vp by Vm? What is Vm is 360, Vp is 60. So FD is given as 510, okay, into this is Vp is 60 and this is 360 the whole square into AP by AM. AP by AM is 36. that it is already given in terms of the geometrical similarity, because the model is 1/6 of the prototype in terms of geometry. So it is 510 into 1 by 36 into 36. So this is equal to 510 Newton. So that should be the answer. So the first question was regarding the velocity of the air in the wind tunnel for testing the model should be 360 km per hour, and the drag force in the actual prototype is the 550 Newton. Okay. What is the next question they asked? They are asking that what is the power requirement to overcome the wind drag of the prototype automobile. Okay, so this is the question number 6. So what it says in that power requirement. So the power requirement to overcome the drag P is equal to the drag force in the prototype into velocity of the prototype, as simple as that. Okay, that is the drag force is 550 Newton into 60 kilometer per hour, right? So it is 60 kilometer per hour. Yes. So 60 into 10 cube divided by 360, that is meter per second, and this is also in Newton. So this is 6, right? So it is 51 by 6 into 10 cube watt. That means 51 by 6 kilowatt. What is 51 by 6? Do you have any calculator? Yeah, so the 51 by 6 will be around what is the answer there? It is given. It is 4.8. Fine. So let me see what they are actually saying. What is 51 by 6? So it is 8.5. 8.5 kilowatt. That's the answer. Yes. Okay. So this is as simple as that. There is nothing difficulty. Now let's move on and we'll go to the next problem. So what's the next problem says? Next problem says a simple approach to consider the effect of particle shape in fluid particle system is through sphericity. So this is a new term. Let me write it down. Sphericity. Okay. consider a cube with each side of 1 micrometer length. The density of this cube shaped particle is 1000 kg per meter cube. Calculate the sphericity of the particle. So before going into the details of the problem, we have to define what is the sphericity of a particle, arbitrary shaped particle. Okay, so sphericity of an arbitrary shaped particle is the ratio of the surface area of a sphere whose volume is the same as the actual particle divided by the surface area of the original arbitrary shaped particle. Okay, so if I have a arbitrary shaped particle, okay, I have given its volume is, let's say, Vp, and surface area is, let's say, AP. Okay, so P represents for the particles. So this is an arbitrary shaped particle. Now, as per the definition, the volume of the arbitrary shaped particles and the volume of the sphere should be the same. So let's say the diameter of the sphere is dp. So what is the volume of the sphere? Of the sphere having diameter d is pi by 6 d cube. Okay, and the volume of both the sphere and arbitrary shaped particle should be the same. Okay, so that means what is the diameter of that means pi by 6 d cube is equal to Vp. So what is the diameter? 6 Vp divided by 6 Vp divided by pi, the whole raised to 1/3. Okay, so area of the sphere is equal to pi d square, right? So what is that? Pi into 6 Vp by pi, the whole to the power 2/3. So what it's coming as? Pi to the power 1/3 6 Vp, the whole to the power 2/3. The sphericity which often represented by phi s, okay, is equal to area of the sphere whose volume is same as the actual particle, okay, which is pi raised to 1/3 6 Vp, the whole raised to 2/3 divided by the surface area, the actual particle AP. That is the definition of the sphericity. Okay, now we will use this. So what is given there in the question? So it's saying that I have a cube So in case of cube, so for a cube with side length A is equal to 1 micrometer. Okay, so what is VP and what is AP? Just we need to do that. So VP is equals to A cube is equal to 1 micrometer cube. AP is equal to 6 square is equal to 6 micrometer square. The phi s is equal to pi raised to 1/3. Then here it is 6 to the power 2/3 divided by 6. Am I right? Yeah. So this is equal to pi by 6 the whole to the power 1/3, I guess. Yeah. What is pi by 6 the whole to the power 1/3? So this is pi by 6 is equal to this whole raised to 1/3. This coming as 0.805996, around something like that. So this is the sphericity of the cube which is given in this case. Fine. Let's move on to the next problem, what it says. So this was question number 7, I guess. Let's move on to the next. Okay, so it looks like very simple. It looks like a very simple problem. Okay, pick the SI unit of surface area from the following. That is meter square. There is nothing great in that. Pick the SI unit of specific surface area. So any specific quantities are always different in terms of like quantity per the quantity by unit mass. Okay, quantity for the unit mass. So specific surface area in this case should also be meter square per kg. Okay, that is the specific surface area. Yeah. Then the problem number 10, which is very simple, I guess. What is given there? It's saying calculate the specific surface area of a spherical silica particle of 1 micrometer diameter and 2000 kg per meter cube density. So what is given here? It is given the diameter of the D is given. D is equal to 1 micrometer. Okay, is equal to 10 raised to minus 6 meter, and density is equal to 2000 kg per meter cube. Fine. So I have to calculate the specific surface area. So what is the value of surface area? Is equal to pi d square. Okay, this is the surface area. Mass of the particle m into rho into pi by 6 d cube. What is rho? Rho is given as 2000. Pi by 6, t is 10 raised to minus 6, that means minus 18 kg. Fine. So the specific surface area is equal to pi into 10 raised to minus 12, that is the actual surface area, divided by 2000 into pi by 6 to 10 raised to minus 18. That should be the answer. So it is 6 into 10 raised to 6 divided by 2000. So 6 into 10 raised to 6, this 3000 meter square per kg. That should be the answer. Okay, fantastic. So we solved almost all the problems. Yeah, we solved all the problems in this case, and yeah, I think it will help you in solving problems in case of your NSEM, because in the NSEM from dimensional analysis and the similarity, the similar type of problems should be there as we expect. So here actually talked about the dynamical similarity and the geometric similarity, dynamic similarity, and the kinematic similarity. All three sorts of similarity should be there in terms of for applying the principles of similarity. Okay, so as we can see, so that means for three types of similarities are there: geometric similarities, which is in terms of the dimensions; kinematic similarity, which actually represent the topology of the motion, okay, and the dynamic similarity, which is in terms of the force. So in order to apply the principles of similarity, all these three condition, that is the models and the prototype, or for the two different problems to be similar, it has to obey the geometrical similarity, kinematic similarity, and the dynamic similarity. Okay, so that's what we can say in this case. Okay, and the in the previous class I think we solved some problem regarding the Buckingham pi theorem, I guess. Yeah, so that is the dimensional analysis. That is again an interesting part to look into. So the principles of similarity and the dimensional analysis, that's a very important part in fluid mechanics. So before of the class, I want to discuss something which is the so this is an interesting. If I mention it here, that so the problem we solved there, only the inertia force and the viscous forces were like only the inertia force and the viscous force were important. Okay, but in like there might be different problems where the forces may not be the only the inertia force and the viscous force. There might be some other different force which is important. So the let me write it one by one. It should be useful, I guess. So let's say for the case 1, you have a Reynolds number is equal to inertia force by viscous force. In terms of symbols, it is rho L V or rho L V by mu, where rho is the density of the fluid, A is the characteristics length scale of the problem, V is the characteristic velocity scale of the problem, and mu is the dynamic viscosity of the problem. Good. The second, we will talk about the Euler number. So here we will represent it by RE. Okay, RE, Reynolds number, RE. Euler number is EU. Okay, this is equal to the pressure force by inertia force. Okay, in terms of symbol, it is delta P by rho V square. Okay, that is the pressure force by inertia force, where delta P is the representative pressure difference, rho is the density of the fluid, and V is the velocity of the fluid. Number 3. Number 3 is the Froude number. Fr is equal to, this is inertia force divided by the gravity force. So what is that? In terms of symbol, this is V divided by L into G, the whole raised to half, where V is the velocity, L is the characteristic length scale, and G is the acceleration due to gravity. Number 4. Number 4 is the Weber number. WB is equal to surface tension force divided by the inertia force. What will be that in terms of symbols? So in terms of symbols, it is sigma by rho v square L, where sigma is the surface tension, okay, and rho v L you already know. Number 5. Number 5 is the Mach number. Is equal to inertia force by elastic force. V by root over of Es into rho, where Es is the elasticity, okay, in terms of Young modulus or something. Es is the elasticity, rho is the density, and V is the velocity. So there might be different non-dimensional number that the ratio of two different flow like associated in the problems. So it is not a big thing, okay. So for a problem to be dynamically similar, all these non-dimensional numbers associated in the problems should be the same. Just like for the problem we solved, we use the condition that the Reynolds number of both the problems must be the same, as well as the drag coefficient should also be the same for both the problems. So there might be problems where you need to equate the Euler number, okay, where the both the pressure forces and the inertia forces are important. So in both the problems you need to equate the Euler number. There might be the problems where the gravity and the inertia force are important. In that case you have to equate the Froude number. There might be the problems where you have the surface tension forces are important, as well as the inertia force is important. In that case you have to equate the Weber number for both the problems. And if the inertia force and the elastic force are important, in that case you have to equate the Mach number of both the problems. So this is just for your yeah, so this is the week 5. So I guess it's fine. So we'll stop here today and again meet on the next Saturday. I think it's 3rd of September. Okay, so again we'll meet in the next Saturday. Thank you.